Hey College Algebra, in this lesson we're going to be looking at section 4.4 and 4.5. We're actually not going to be looking all too much at 4.4. We're going to skip these applications of logarithms and applications of natural logarithms. We're just going to be looking at these three things today. We're going to be looking at common logs and natural logarithms, and then logarithms with other bases. So here's the common logarithm. For all positive numbers x, log of x is equal to log base 10 of x. So if we have written log of x, it is understood that this base right here that's not written is 10. We can write it either way. Okay. And this is just telling us in the common log, the button on your calculator that says log is understood that it is the base 10 logarithm. So this is how we're going to use it in this section. We're going to be using the calculator to find the values of our logarithms here. We're asked to find log of 10,000. Well, log of 10,000, if you plug that into your calculator, you will end up getting 4. And then log of 341, plug that into your calculator just like this, and this is our decimal approximation of that. Same goes with this logarithm right here. We're going to get, this is our solution here. Okay, this right here is our natural logarithm. Again, for all positive numbers x, ln of x is equal to log base e of x. So instead of writing log base e of x, you will often see me write, or in your book in problems, this logarithm right here written as ln of x. You also have a key on your calculator that says ln, and so that is what you're going to be using on your calculator to help you find values for each of these logarithms right here. So in here, this was supposed to be 4, got cut off, but anyway, ln of e to the 4th, type that into your calculator and you will get this value right here, 4. And then ln of 341, here's our value. And then ln of this decimal number here, we get this approximation value right here. Okay, so let's look at some other things. All right, so that's how we're going to be using our calculators to help us. We're going to be using it to help us find values of natural logarithms and common logarithms. But sometimes we need to find other logarithms that have other bases. And to do that, we're going to be using something called a change of base. And we have a change of base formula that we're going to be using. And actually, some calculators do allow you to type in the base of your logarithm. And I can show you that in class. So right here is the change of base theorem, but this right here is also called the change of base formula. So to change our base to anything that we want, and most of the time we want to change it to log base 10 because that's what most of our calculators have. So really this formula actually looks like this for us. Log understood base 10 of our x value over log base a. And so that's how we're going to use it in order to figure out our logarithms that we have in our calculators. Also, we can do the same thing. We get with the ln, the natural log. We could say ln of x over ln of a, and these would actually give us the same values that we are looking for. Alright, this example has asked us to use the change of base theorem or formula to find the approximation to 4 decimal places for each logarithm. So we have this logarithm and the next to look at. Alright, so this is how the change of base formula goes. If we have log base 5 of 17, it can be rewritten as log base 10, it's understood to be base 10, of 17 over log 5. So take this number, place it in here first, and then this number is next. So log 17 over log 5, that ends up giving us the approximation. It's approximately 1.7603. And we're done with that one. In this next example, part B of the same question, we're asked to use the change of base theorem or formula to approximate this to 4 decimal places. Again, use that change of base formula. This time I'm just going to use ln instead of log, because we have the use of ln or log base 10 on our calculator. We can say ln of 0.1 over ln of 2. This will give us the same value as log of 0.1 over log of 2. Those will give us the same exact values. And that is approximately, let me see what my calculator says, negative 3.3219. And that is it on using the change of base formula. So now we're to section 4.5. We're going to be solving exponential and logarithmic equations. Let's go and get started. Alright, so we're going to be using this property of logarithms to help us in solving exponential equations and logarithmic equations. This right here holds true that if we have log base a of x equals log base a of y, remember these bases have to be the same in order to use this property, then we can just set what's inside our logarithms, x equal to y, which is what is stated over here. So we're going to be using that property to help us in solving this logarithm right here. We have 8 to the x equals 21, and in order to solve this, there is no number that we can change our bases to. There is no 8 to the power of some number equals 21. So we can't use things that we did in the previous section, like I showed you to solve exponential equations. We have to use our logarithms, because this right here, we need to extract this x, or exponent, and bring it down. And that's where our logarithms come in handy. So let's take the log of both sides of our equation. So we're going to say log 8 to the x equals log of 21. And then now, to get x down from being an exponent, that is why we're using our logarithms here. We're going to take our exponent and use one of our properties and move it down in front of our log. So we get x times log of 8 equals log of 21. We're almost done at this point. Now to get x by itself, we just simply divide both sides by log of 8. And that gets rid of this, and we're left with x equals log of 21 over log of 8. Now if I asked you to leave it in exact form, this is that form right there. Don't change anything. But we're asked to give the solutions to the nearest thousand. So that's 3 decimal places. And what my calculator tells me is 1.464. And we are done. Okay, in that previous exercise, we ended up with an answer or a solution similar to this right here. And please, this is why I have this caution. Please don't confuse this with our logarithm of 12 over 7. These two things do not equal each other. All right, to solve this exponential equation, let's do the same thing that we just did in the previous problem. We're going to take the log of both sides of our equation. So log of 5, 2x minus 3 equals log of 8 to the x plus 1. So we do this in order to use one of our log properties that we need to use to take this down from being an exponent. So move your exponents down. Make sure you put it in parentheses. Now the next step on this right here is to distribute our logarithm out across the set of parentheses. Here we get 2x times log of 5, and then minus 3 log of 5, and that's equal to x log of 8 plus just log of 8. Now we're going to gather on one side of our equation all of the terms that have x in it, so we can factor out an x from those. So keep this on this side of the equation, but subtract this on both sides of the equation. And then we're going to add that to the other side. Get 2x log of 5 minus x log of 8. And that is equal to log of 8 plus 3 log of 5. And we're almost done. Now we can factor out this x, so we only have one x value. And then to get x all by itself, at this point, what we're going to do is divide. Divide both sides by this whole thing in parentheses here, the 2 log of 5 minus 2, or just log of 8. Okay, and that cancels this out on this side, and we're left with x equals this right here. This is our exact solution, but we're asked to give the solution to the nearest thousandth. So x is equal to, let's see what my calculator says, 6.062. And we are done. All right, to solve this exponential equation, since we have base e, we're going to be using our natural logarithm to help us in canceling things out. But before we do that, we're going to put together this and this right here using our exponential properties. Remember, if we have the same base like we do here in both of these exponential expressions, we are going to put together the powers by adding them together. So we get e to the 4x plus x minus 1. So 4x plus x gives us 5x, then minus 1. That's equal to 5e. So now the next step on this one is to take the natural log of both sides. Let's see. Okay, on this one right here, we're going to first bring this down. And then this right here stays the same. Okay, so on this one, what we're going to do is I'm going to tell you that ln of e, that there is going to be 1. If you put that in your calculator, ln of e, it turns out to be 1. So we have on this side 5x minus 1, and it's going to equal, again, ln of e is 1. So how I'm going to show you to do this, we have to use, again, our logarithmic properties. This is going to be like saying ln of 5 plus ln of e. So we have, again, 1 right here. So I'm going to subtract 1 on both sides to get 5x minus 2 equals ln of 5. And now to solve for x, just like a regular equation, treat this as a number because it is a number. We just say subtract 2 from both sides to get 5x equals ln of 5 minus 2. And divide both sides by 5 to get this right here. And that is our exact value of x. And to find the solution to 3 decimal places, plug that into your calculator appropriately, please. And what I mean by that is you're going to need to put parentheses around ln and then a 5, and don't mistakenly put it around the 2, because that is separate from the ln, or the natural log. But here we get an approximation of 0.722. There we go. Alright, so the solution for this one is going to rely on things that we've learned in previous chapters. What we have here is a quadratic-like equation. What I'm going to do here is say let's rewrite this first. I can rewrite this as what I just rewrote here, e to the x, then raised to the 2. I'm going to say let u equal e to the x. And now what we're going to do is replace our e to the x with u. And now we have a quadratic to solve. So in our quadratic, this is what we're going to do. We're going to factor first. So this factors to u minus 1 times u minus 5. And so we get the solutions from it. We get u is equal to 1 and 5. So now what we're going to do is, since u is equal to 1 or u is equal to 5, we're going to substitute what u is equal to, which is e to the x, back in for u. And solve. So take the ln of both sides of our equation, and then this brings our exponent down, and ln of e is equal to 1, so this is actually just equal to x, and ln of 1, that is equal to 0. So here's one of our solutions to our equation. And then the next solution is very similar. Take the ln of both sides, and that brings our exponent down, and ln of e is 1, so x is equal to ln of 5. And that's our solution for that one. Again, if we're asked to find to the nearest thousandth, then approximate the number to the nearest thousandth, like this says. But right now, I'm just going to keep it as that. Those are our two solutions for this exponential equation. Okay, on these two equations of logarithmic equations, we're going to be using this definition to help us in solving our logarithms, like we've done in the previous section. But let's see, on this first one, before we do that, before we change our logarithmic equation to its exponential form, let's change this up a little bit. We're going to divide both sides by 4 first. So we want to get our logarithm all by itself before we change it into its exponential form. So get ln of x equals 9. Another way to look at ln of x is like this right here. Remember, it's log base e of x equals 9. Now change this right here into its exponential form. And what that's going to look like is x equals e to the 9th. And that right there is our solution, e to the 9th. And it's asked us to give exact values, so leave it as e to the 9th and don't change it to its decimal form, because that's it right there. Okay, let's look at part B. This logarithm is all by itself. There's no number in front that's being multiplied, so no division or anything. We just need to simply change this logarithmic equation into its exponential form. So I take our base, which is 3, and we do this. We're going to say, 3 to the first equals what's inside our logarithm, which is x to the third minus 5. So that changes it to its exponential form. 3 to the first is just 3. So subtract or add 5 to both sides at this point, and we get 8 is equal to x to the third. To get x all by itself, take the cube root of both sides of our equation, and we get x is equal to 2. And we are done. In this example, we're going to use the fact that, or the property that log base a of x is equal to log base a of y means that we can set what's inside the logarithms equal to each other. We can say x is equal to y. So for this one right here, the first thing that we need to do is condense each side of our equation. So put together these two logarithms right here with our logarithmic properties. Since this right here, we have two logs being added together, that means what's inside our logarithms are going to be multiplied together. We have log, I'm going to go ahead and multiply them, of 2x squared plus x. And there's nothing to do to the other side of the equation. We're just going to keep it as log of x plus 8 because that's a single logarithm on this side of the equation. Now, using this property up here, we're going to set what's inside our logarithm equal to each other and solve for x. And now solve for x. Just we're going to subtract x from both sides to get this. Divide both sides by 2. And now take the square root of both sides of our equation. And we get plus or minus 2. Okay. And at this point, what you need to do is check to see if both solutions actually work back into your equation. You're going to plug negative 2 and 2 back into this original equation up here. And when we do that for the value of negative 2, we plug it in here, we're going to get an error. So this means We're not going to be using the -2 for this one, for this equation right here. So our only solution is actually x equals 2, because the solution of 2 does work in this equation. Okay, so it says pretty much the same thing I just told you about checking solutions. Recall that our domain for this logarithm is from 0 to -8. So this is the reason why whenever you plug that -2 back into log of x, it ends up giving us an error or no solution. It's because our domain is only from 0 to infinity, only positive numbers. So let's look at the last example. In this last example I have for you, what we're going to do is, just like the last one, we're going to combine these two logarithms with our logarithmic properties, but then we're going to be using this equivalent right here to help us in solving for x. So let's do that. Let's combine our logarithms. So because of this being a plus sign, we're going to multiply what's inside our parentheses to get one logarithm. I'm actually just going to keep it like this. X minus 5 times x minus 3. That is equal to 3. Now let's change it to its equivalent form. Change it to its exponential form. So we have base 2, that goes in for a. And we have, okay, this is our x, so keep that. It's 2x minus 5 times x minus 3. And that is equal to 2 to the third. Now we have a quadratic equation to solve. And how we're going to do that is by multiplying this all out and setting it equal to 0. So we have this right here. We're going to say, let's do all the foiling to get this right here. Plus 15. That is equal to 8. We need to multiply this all out first so we can subtract 8 from both sides and have a quadratic that is set equal to 0. Now we can either factor or use the quadratic formula at this point. And since this thing does not factor, we're going to have to use the quadratic formula. And let's do that. We get negative 11, so just positive 11, and plus or minus 11 squared, or negative 11 squared, minus 4ac, all over 2a. Now this reduces to this right here. 11 plus or minus square root of 65, 2a, and 2 times 2. So over 4. Now, at this point, we need to check both of our solutions. So, plug back up into this problem right here. For x value, 11 plus square root of 65 over 4 to see if that solution works. and gives us a 3. And then do the same thing with 11 minus square root of 65 over 4. And whenever we plug in the 11 minus square root of 65 over 4, we're actually going to get an error because it's a negative number. And so we're going to reject that solution and say our only solution is x equals 11 plus square root of 65 over 4. And we are done. So, like I said, we're done. That is the end of this lesson and the end of college algebra. So I will see you in class. Goodbye, everybody.